In part 4 of lecture 2, we will talk about going from finite automata to scanners. We use the Greek letter epsilon to represent an empty string, and an empty string is exactly what the name implies, a string of text that has absolutely nothing in it. An epsilon string is where our transition occurs based on nothing. I know this sounds a little confusing, but it is like falling into a manhole without a cover on it. But it has some value. It means that we can just go into another state without having to encounter a character. In the NFA shown on the slide, we can handle as many zeros as we wish or need, whereupon we will move to the next state, Q1, and then process as many ones as we wish or need, following by another slide into Q2, the final state, where we will process an indefinite number of twos. All this means is that we can go from state to state without reading anything else. Non-deterministic finite automata with epsilon moves can be converted to NFAs without epsilon moves. We need to find the epsilon closure of state Q, which consists of all states which can be reached from state Q by one or more epsilon moves. The question is, why are deterministic finite automata, non-deterministic finite automata, and non-deterministic finite automata with epsilon moves so important? We can automate the process of constructing a non-deterministic finite automaton with epsilon moves based on a given regular expression. From there, I can build a non-deterministic finite automaton without epsilon moves. And from that, in turn, I can build a deterministic finite automaton. Computers being deterministic devices, I need the deterministic finite automaton if I'm looking to create a program to emulate this process. This also means that now, given the lexical requirements of a programming language, I can build a scanner for it. Let's take a look at a few basic finite automata. In the two cases, I have regular expressions that are one character long. On the left, 0, and on the right, 1. In both cases, I have an initial state transitioning on that one character to a final state. I can have the computer put these together to form a non-deterministic finite automaton for the sequence 0, 1 by taking these two basic automata and connecting them with an epsilon move. Here we have two additional non-deterministic finite automata based on the simple cases that we had before. Here I have it on the top. My regular expression is 0 plus 1, which means either 0 or 1. I have the two simple machines in parallel, connected on either end by an initial state on the left and a final state at the end. You'll notice that in both cases, I have a pair of epsilon moves taking me on the left from the initial state to one of the two parallel tracks, and on the end, bringing the two parallel tracks back to a final state. The one on the bottom is a little more complicated. I'm going to have 1, 0 or more times. So I start off with the basic machine where I have a transition from that takes place over 1. I have it connected by an epsilon move to an initial state on the left and to a final state on the right. I have two additional epsilon moves, one taking me from Q2 back to Q1, so I can have yet another 1. I also have an epsilon state from the initial state to the final state to cover the case where there are 0 occurrences of 1. And this can be built fairly easily by a computer program from the basic part that we had before. We're now going to combine all of these in one sense. We're going to build a state machine for the regular expression 0, 1 asterisk plus 1. The 1 is fairly simple. I have a path along the top where I have an epsilon move taking me from Q0 to Q1. I go from on 1 from Q1 to Q2, and on another epsilon move from Q2 to Q9 at the end. I also need to deal with the 0, 1 asterisk. So from Q0, I have an epsilon move to Q3, and on 0, that takes me to Q4. So much for the 0. The 1 asterisk is a little more complicated. I have a 0 move taking me from Q4 to Q5, and an epsilon move taking me past everything to Q8. That would cover the situation of 0 occurrences of 1. A different epsilon move takes me from Q5 to Q6. Now I have on 1 a move from Q6 to Q7, and an epsilon move back to Q6 so I can repeat it. On the right of Q7, I have an epsilon move to Q8, and another epsilon move to Q9. While this is clearly more complicated than we saw before, this is a non-deterministic finite automaton that can be constructed from the regular expression by the computer. And this shows that we can automate the process of building a scanner if we choose to do so. Now that we've looked at the theory behind using finite automata to analyze the stream of characters to produce strings that are meaningful to the program, let's take a look at a special form of finite automata, one that plays a more practical role in terms of a scanner: transition diagrams. Their special form, they incorporate features that belong in a compiler scanner. First thing we need to consider are the actions associated with final states. This is something that we will take a good look at in a few moments. We also have a backup from the state. This allows a look-ahead character to be returned to the input stream for when we start scanning for the next lexeme. Transitions can also be labeled as belonging to other, indicating any class of character that is not explicitly accounted for. When we draw a transition diagram, it will be a lot more useful to use a slightly different approach to describing regular expressions. This is borrowed from BNF, Backus-Nahr form, which we'll talk about more when we get up to syntactic analysis. A vertical line B indicates A or B. And as before, AB indicates A followed by B. If I have AB in parentheses with an asterisk afterwards, that means the A followed by B and that sequence repeated 0 or more times. If I have the A and B in parentheses with a vertical line in between, that means I will have either A or B, and then, as you can see here, it will be followed by C. This notation allows us to create lexical categories or classes. In this slide, you'll see that we create a class called letter that includes all 26 letters from A to Z in both lowercase and capital. We can include all 10 digits and a variety of punctuation that we might use in a programming language. We can define an identifier as a letter followed by 0 or more occurrences of a letter or digit. We can define an integer as a digit followed by 0 or more digits. We can define a real as a digit followed by 0 or more digits, punctuation period, and then a digit followed by 0 or more digits. We can also have it written so that we have what we saw before: an E in lower or capital form, a plus sign, a minus sign, or no sign at all, followed by a digit, followed by 0 or more digits. In this way, we have defined identifiers and the numbers that we're looking to use. Let's take a look at an example of a transition diagram. You'll notice I have a state 0 labeled simply with a 0. On a letter, I will transition to state 1, and I will remain there as I keep reading letters and digits. Once I run into something that is not alphanumeric, I will go to state 2. In doing so, I will push back the look-ahead character into the character stream, and I will recognize that this string represents an identifier. On the other hand, if I encounter a digit when I am in state 0, I'll go to state 3, and I will remain there as long as I am encountering digits one after the other. Once I encounter a letter or a different type of character, non-alphanumeric, I will go to state 4. The asterisk again tells me I will push back the look-ahead character onto the input stream, and this is going to be labeled as a number.